Now, to experimentally work out what the heat exchange is and enthalpy is, we use this equation Q equals mc delta T. So specific heat is the C. Specific heat is a characteristic of a substance, such as metals have a very low specific heat. They don't take much energy to heat up, and they very quickly, and they don't release much energy, and they cool down quite quickly. And that's because there's lots of electrons moving around, and it's very easy to get to the kinetic energy with those substances. For stuff like that's more of a conductor like wood, that's got lots of covalent bonds, everything is locked in place, air spaces. It takes quite a lot of energy to raise the temperature, and it releases quite a lot of energy when it moves down. And so we normally use water because we almost always use water. The physicists will use lots of different things because our chemical reactions are happening mainly in water. So that's 4.18 kilojoules per mole. You'll have that in your data booklet. And so we're going to use that as the specific heat. And so when we do our reaction, we grab a certain amount of water and work out the temperature change. And if the temperature has gone up quite a bit, we times out all those numbers together to work out how much the heat has changed. And if the temperature hasn't risen much, well, obviously that we haven't had a large temperature change. Or if it goes down, vice versa when it goes down. Now, to get that per mole, to get it to enthalpy, we have to work out how many moles of the various chemical was involved, and we divide it by that number of moles, and that'll give us this standard value that's enthalpy. So we can go to a couple of, get more specific now. So we normally do it, there are the numbers that we spoke about before. So a mil, a centimeters cubed, is the equivalent of a gram. So you write that down as your assumption. There's the 4.18. And I'm not quite sure what the mass is in this particular instance. Now, we usually do our best to surround it with insulating material so all of the heat goes into the water and doesn't escape, and also make sure it's fairly even. So we have a stirrer and, of course, the thermometer. So this is a very basic setup. You might have even more basic setup, just have a beaker, which is quite fine. Or you may have something a little bit more expensive, who knows. Okay. So very importantly, this is a super typical question. I dare say it's going to be in most tests. Where are the assumptions? Where are the errors? So this is the big one. The heat is lost to the surroundings or gained from the surroundings if it's actually a reaction that cools down, but then it ends up heating up because it absorbs other things. Also have a careful look at whether your reaction involves gas and maybe you're losing heat that way. And there are other errors here. Thermometer precision error on the thermometers, that's more minor. Okay, so this also happens in reverse with endothermic reactions. Right here we're looking at an exothermic reaction. So you're going to do one of these as your mandatory pracs, and you're going to have to do this as well. So you always let it sit stable for a while, and this is the point where you add chemical to it. So what happens is it takes a while for the reaction to occur. It doesn't just automatically happen. If it automatically happened, it would actually hit here. But as the reaction happens, you're actually losing temperature, and you can work that out when the reaction finishes to see how quickly it cools down. Not completely accurately, because actually the temperature curve from 100 is actually a little bit exponential. So it could actually be even worse than what you're thinking. But anyway, this is how we do it. So we do a line of best fit here, and then we work out where you started the reaction and where that line would have traveled. And then you draw a line across here to see where that is. And that's the actual temperature that it should have reached if it didn't take this extra time. It was cooling down during that time. So the delta H is actually not going to be here. It's not going to be this point to this point. It's actually going to be this point to this point. So it's important you do that for the delta T. So we're just going to do some problems here. So first of all, we've got 1,200 kilojoules of heat evolved when 2 moles of magnesium react with 1 mole of oxygen. We draw out the formula for that, and 2 moles of magnesium plus 1 mole of oxygen is actually the balanced reaction. So that's actually the delta H of that reaction is 1,200 kilojoules. And so the question is, how much energy is released if you burnt this much magnesium? So the actual delta H of magnesium is not actually 1,200. That's the delta H of the reaction. So that's when everything's balanced out. So if we're going to do delta H of magnesium, we've got to divide it by 2 because delta H is per mole. So this is per mole of the balanced reaction. This is just per mole of magnesium. So it's actually minus 600 kilojoules per mole just for the magnesium. And if we have 0.6 grams of magnesium, so number of moles is mass on molar mass. So the mass is 0.6, the molar mass of magnesium is 24.3. So that gives us 0.0247 moles of magnesium. So that's how many moles of magnesium we used. And that's how much energy would be released if you use 1 mole of magnesium. So we go back to that previous formula on a previous slide. Delta H is the heat divided by number of moles. So if we're trying to work out the heat, because we know the delta H is minus 600, it's minus 600 by 0.0024 moles. So we get 14.8 grams of heat is actually released if we didn't use molar values. We used 0.6 instead of 1. Okay, so definitely a little bit tricky. All right, let's go to problem 2. So problem 2, so we have 20 mils of 2 molar sodium hydroxide and 30 mils of HCl. That's also 2 molar. The temperature increases by 12. Determine the heat released. Now, because the temperature increases by 12, it doesn't matter if it's in Kelvin or degrees Celsius. It's going to be the value 12. And so this value here is 12. We're all good with that. The C never changes, 4.18. And you've put 20 plus 30. These chemicals are dissolved in water, and so that adds up to a total of 50 mils. So that's 50 grams. Okay, and so just here I've just stated that here. So it is a total volume of 50 mils. Therefore, it is total 50 grams. That's an assumption. It's always you always need to write your assumptions out there, especially for this one. And so times in all those numbers out, we do get our Q. So that's 2,508 joules. Okay, and I'm just going to leave it there. There is an extension to problem 2. So problem 2 could ask you for the enthalpy, which would be quite nasty. As you can see here, what you would have to do is actually work out what is the limiting reagent. And then, so sodium hydroxide happens to be the limiting reagent in this one. And so then you know what to divide that value by. And then you'll get the actual enthalpy of that reaction. So that's a lot nastier.